In mathematics, a ratio is a relationship between two numbers indicating how many times the first number contains the second. For example, if a bowl of fruit contains 8 oranges and 6 lemons, then the ratio of oranges to lemons is 8 to 6. Thus, a ratio can be a fraction as opposed to a whole number. Also, in this example the ratio of lemons to oranges is 6 to 8, and the ratio of oranges to the total amount of fruit is 8:14. The numbers compared in a ratio can be any quantities of a comparable kind, such as objects, persons, lengths, or spoonfuls. A ratio is written A to B, or A, B, or sometimes expressed arithmetically as a quotient of the two. When the two quantities have the same units, as is often the case, their ratio is a dimensionless number. A rate is a quotient of variables having different units. But in many applications, the word ratio is often used instead for this more general notion as well. Notation and terminology. The ratio of numbers A and B can be expressed as the ratio of A to B. A is to B. A, B. A fraction, that is the quotient. A divided by B, which can be expressed as either a simple or a decimal fraction. The numbers A and B are sometimes called terms, with A being the antecedent and B being the consequent. The proportion expressing the equality of the ratios A, B and C, D is written A, B equals C, D, or A, B, C, D. This latter form, when spoken or written in the English language, is often expressed as A is to B as a C is to D. A, B, C and D are called the terms of the proportion. A and D are called the extremes, and B and C are called the means. The equality of three or more proportions is called a continued proportion. Ratios are sometimes used with three or more terms. The ratio of the dimensions of a 2x4, that is 10 inches long, is 2:4:10. A good concrete mix is sometimes quoted as 1:4 for the ratio of cement to sand to gravel. For a mixture of 4/1 cement to water, it could be said that the ratio of cement to water is 4:1, that there is 4 times as much cement as water, or that there is 1/4 as much water as cement. History and etymology. It is impossible to trace the origin of the concept of ratio, because the ideas from which it developed would have been familiar to proliterate cultures. For example, the idea of one village being twice as large as another is so basic that it would have been understood in prehistoric society. However, it is possible to trace the origin of the word ratio to the ancient Greek lambda omicron gamma omicron sigma. Early translators rendered this into Latin as ratio. A more modern interpretation of Euclid's meaning is more akin to computation or reckoning. Medieval writers used the word proportia to indicate ratio and proportionalitas for the equality of ratios. Euclid collected the results appearing in the elements from earlier sources. The Pythagoreans developed a theory of ratio and proportion as applied to numbers. The Pythagoreans' conception of number included only what would today be called rational numbers, casting doubt on the validity of the theory in geometry where, as the Pythagoreans also discovered, incommensurable ratios exist. The discovery of a theory of ratios that does not assume commensurability is probably due to Eudoxus of Cnidus. The exposition of the theory of proportions that appears in Book 7 of the Elements reflects the earlier theory of ratios of commensurables. The existence of multiple theories seems unnecessarily complex to modern sensibility since ratios are, to a large extent, identified with quotients. This is a comparatively recent development, however, as can be seen from the fact that modern geometry textbooks still use distinct terminology and notation for ratios and quotients. The reasons for this are twofold. First, there was the previously mentioned reluctance to accept irrational numbers as true numbers. Second, the lack of a widely used symbolism to replace the already established terminology of ratios delayed the full acceptance of fractions as alternative, until the 16th century. Euclid's Definitions Book V of Euclid's Elements has 18 definitions, all of which relate to ratios. In addition, Euclid uses ideas that were in such common usage that he did not include definitions for them. The first two definitions say that a part of a quantity is another quantity that measures it, and conversely, a multiple of a quantity is another quantity that it measures. In modern terminology, this means that a multiple of a quantity is that quantity multiplied by an integer greater than 1, and a part of a quantity is a part that, when multiplied by an integer greater than 1, gives the quantity. Euclid does not define the term measure as used here. However, one may infer that if a quantity is taken as a unit of measurement, and a second quantity is given as an integral number of these units, then the first quantity measures the second. Note that these definitions are repeated, nearly word for word, as definitions 3 and 5 in Book 7. Definition 3 describes what a ratio is in a general way. It is not rigorous in a mathematical sense, and some have ascribed it to Euclid's editors rather than Euclid himself. Euclid defines a ratio as between two quantities of the same type. So, by this definition, the ratios of two lengths or of two areas are defined, but not the ratio of a length and an area. Definition 4 makes this more rigorous. It states that a ratio of two quantities exists when there is a multiple of each that exceeds the other. In modern notation, a ratio exists between quantities p and q if there exist integers m and n, so that mp greater than q and nq greater than p. This condition is known as the Archimedes property. Definition 5 is the most complex and difficult. It defines what it means for two ratios to be equal. Today, this can be done by simply stating that ratios are equal when the quotients of the terms are equal. But Euclid did not accept the existence of the quotients of incommensurate, so such a definition would have been meaningless to him. Thus, a more subtle definition is needed where quantities involved are not measured directly to one another. Though it may not be possible to assign a rational value to a ratio, it is possible to compare a ratio with a rational number. Specifically, given two quantities, p and q, and a rational number m, n, we can say that the ratio of p to q is less than, equal to, or greater than m, n when np is less than, equal to, or greater than mq respectively. Euclid's definition of equality can be stated as that two ratios are equal when they behave identically with respect to being less than, equal to, or greater than any rational number. In modern notation, this says that given quantities p, q, r and s, then p, q, r, s if for any positive integers m and n, np less than mq, np equals mq, np greater than mq according as near less than ms, near equals ms, near greater than ms respectively. There is a remarkable similarity between this definition and the theory of dedekind cuts used in the modern definition of irrational numbers. Definition 6 says that quantities that have the same ratio are proportional or in proportion. Euclid uses the Greek nu alpha lambda omicron gamma omicron nu. This has the same root as lambda omicron gamma omicron sigma and is related to the English word analog. Definition 7 defines what it means for one ratio to be less than or greater than another and is based on the ideas present in definition 5. In modern notation, it says that given quantities p, q, r and s, then p, q greater than r, s if there are positive integers m and n, so that np greater than mq and nim as with definition 3, definition 8 is regarded by some as being a later insertion by Euclid's editors. It defines three terms p, q and r to be in proportion when p, q, q, r. This is extended to four terms p, q, r and s as p, q, q, r, r, s, and so on. Sequences that have the property that the ratios of consecutive terms are equal are called geometric progressions. Definitions 9 and 10 apply this, saying that if p, q and r are in proportion then p, r is the duplicate ratio of p, q, and if p, Q, R and S are in proportion, then P, S is the triplicate ratio of P, Q. If P, Q and R are in proportion, then Q is called a mean proportional to P and R. Similarly, if P, Q, R and S are in proportion, then Q and R are called two mean proportionals to P and S. Number of terms and use of fractions. In general, a comparison of the quantities of a two-entity ratio can be expressed as a fraction derived from the ratio. For example, in a ratio of 2 to 3, the amount, size, volume, or quantity of the first entity is that of the second entity. If there are 2 oranges and 3 apples, the ratio of oranges to apples is 2 to 3, and the ratio of oranges to the total number of pieces of fruit is 2 to 5. These ratios can also be expressed in fraction form. There are 2/3 as many oranges as apples, and 2/5 of the pieces of fruit are oranges. If orange juice concentrate is to be diluted with water in the ratio 1 to 4, then 1 part of concentrate is mixed with 4 parts of water, giving 5 parts total. The amount of orange juice concentrate is 1/4 the amount of water, while the amount of orange juice concentrate is 1/5 of the total liquid. In both ratios and fractions, it is important to be clear what is being compared to what, and beginners often make mistakes for this reason. Fractions can also be inferred from ratios with more than 2 entities. However, a ratio with more than 2 entities cannot be completely converted into a single fraction, because a fraction can only compare 2 quantities. A separate fraction can be used to compare the quantities of any 2 of the entities covered by the ratio. For example, from a ratio of 2, 3, 7 we can infer that the quantity of the second entity is that of the third entity. Proportions and percentage ratios. If we multiply all quantities involved in a ratio by the same number, the ratio remains valid. For example, a ratio of 3 to 2 is the same as 12 to 8. It is usual either to reduce terms to the lowest common denominator, or to express them in parts per hundred. If a mixture contains substances A, B, C and D in the ratio 5, 9, 4, 2, then there are 5 parts of A for every 9 parts of B, 4 parts of C and 2 parts of D. As 5 plus 9 plus 4 plus 2 equals 20, the total mixture contains 5/20ths of A, 9/20ths of B, 4/20ths of C, and 2/20ths of D. If we divide all numbers by the total and multiply by 100%, we have converted to percentages. 25% A, 45% B, 20% C, and 10% D. If the 2 or more ratio quantities encompass all of the quantities in a particular situation, it is said that the whole contains the sum of the parts. For example, a fruit basket containing 2 apples and 3 oranges and no other fruit is made up of 2 parts apples and 3 parts oranges. In this case, or 40% of the whole is apples and or 60% of the whole is oranges. This comparison of a specific quantity to the whole is called a proportion. If the ratio consists of only 2 values, it can be represented as a fraction, in particular as a decimal fraction. For example, older televisions have a 4 to 3 aspect ratio, which means that the width is 4/3 of the height. This can also be expressed as 1.331 or just 1.33 rounded to 2 decimal places. Modern widescreen TVs have a 16 to 9 aspect ratio, or 1.78 rounded to 2 decimal places. One of the popular widescreen movie formats is 2.351 or simply 2.35. Representing ratios as decimal fractions simplifies their comparison. When comparing 1.33, 1.78 and 2.35, it is obvious which format offers wider image. Such a comparison works only when values being compared are consistent, like always expressing width in relation to height. Reduction. Ratios can be reduced by dividing each quantity by the common factors of all the quantities. As for fractions, the simplest form is considered that in which the numbers in the ratio are the smallest possible integers. Thus, the ratio 40 to 60 is equivalent in meaning to the ratio 2 to 3, the latter being obtained from the former by dividing both quantities by 20. Mathematically, we write 40 to 60 equals 2 to 3, or equivalently 40, 60, 2, 3. The verbal equivalent is 40 is to 60 as 2 is to 3, a ratio that has integers for both quantities and that cannot be reduced any further is said to be in simplest form or lowest terms. Sometimes it is useful to write a ratio in the form 1x or x1, where x is not necessarily an integer, to enable comparisons of different ratios. For example, the ratio 4 to 5 can be written as 1.25. Alternatively, it can be written as 0.81. Where the context makes the meaning clear, a ratio in this form is sometimes written without the 1 and the colon, though, mathematically, this makes it a factor or multiplier. Irrational ratios. Some ratios are between incommensurable quantities, quantities whose ratio is an irrational number. The earliest discovered example, found by the Pythagoreans, is the ratio of the diagonal to the side of a square, which is the square root of 2. The ratio of a circle's circumference to its diameter is called pi, and is not only irrational but also transcendental. Another well-known example is the golden ratio, which is defined as both sides of the equality a, b equals a. Writing this in fractional terms as finding the positive solution gives the golden ratio, which is irrational. Thus at least one of a and b has to be irrational for them to be in the golden ratio. An example of an occurrence of the golden ratio is as the limiting value of the ratio of two successive Fibonacci numbers. Even though the nth such ratio is the ratio of two integers and hence is rational, the limit of the sequence of these ratios as n goes to infinity is the irrational golden ratio. Similarly, the silver ratio is defined as both sides of the equality a, b equals a. Again, writing it in fractional terms and obtaining the positive solution, we obtain which is irrational. So if two quantities a and b in the silver ratio, at least one of them must be irrational. Odds. Odds are expressed as a ratio. For example, odds of 7 to 3 against mean that there are 7 chances that the event will not happen to every 3 chances that it will happen. The probability of success is 30%. In every 10 trials, there are expected to be 3 wins and 7 losses. Units. Ratios may be unitless, as in the case they relate quantities in units of the same dimension, even in their units of measurement are initially different. For example, the ratio 1 minute, 40 seconds can be reduced by changing the first value to 60 seconds. Once the units are the same, they can be omitted, and the ratio can be reduced to 3 to 2. On the other hand, there are non-dimensionless ratios, also known as rates. In chemistry, mass concentration ratios are usually expressed as weight-volume fractions. For example, a concentration of 3% with V usually means 3 grams of substance in every 100 milliliters of solution. This cannot be converted to a dimensionless ratio, as in weight or volume fractions. Triangular coordinates. The locations of points relative to a triangle with vertices A, B, and C and sides AB, BC, and CA are often expressed in extended ratio form as triangular coordinates. In barycentric coordinates, a point with coordinates is the point upon which a weightless sheet of metal in the shape and size of the triangle would exactly balance if weights were put on the vertices, with the ratio of the weights at A and B being the ratio of the weights at B and C being and therefore the ratio of weights at A and C being in trilinear coordinates. A point with coordinates x, y, z has perpendicular distances to side BC and side CA in the ratio x, y, distances to side CA and side AB in the ratio y, z, and therefore distances to sides BC and AB in the ratio x, z. Since all information is expressed in terms of ratios, A triangle analysis using barycentric or trilinear coordinates applies regardless of the size of the triangle.